Alright, so in this video I'm going to give you a very quick and super easy intro to first time using the Yocto project. We're going to see how to obtain the source code, how to build our first target, which is going to be a QEMU x86 64-bit emulator. We're going to talk about a little bit of pitfalls and some things that may happen like for the first couple of times. And because the Yocto project requires a lot of disk space, requires quite a lot of bandwidth to get first set up with. I'm not talking about when you first get the Yocto project code itself, but rather when you actually want to build software for whatever target you are interested in. And because it takes a lot of time if you do not have like a strong computer, then many people would want to actually build the Yocto project on strong build servers or on, let's say, AWS or GCE or Azure. So what we're going to do here is also show some of the pitfalls that happen over there. So in order to start with the Yocto project, you're going to go to yoctoproject.org, and then this is how the web page would look like. You would have a couple of versions like Warrior, FOD, and Sumo, where the recent version is actually going to be named Zeus, the latest and greatest one. So we're going to go, you have here all capabilities, get started here, and you have the new to the project, which is something you would really want to click and read through the first time you actually get to it. And if you're already experienced, as I am, or as a lot of you may be, then you're going to just go to the latest and greatest or whatever version you need. Now you can get it via Git, clone it, and you can go ahead and download a tarball. So we're going to go copy it, and then we're going to wget the tarball that we're interested in. It is Pokey Zeus and the version. So we downloaded it. We can see that the tarball is 90 megs for the Zeus version, and we're going to extract it. And once we extract it, it's not going to take a long time. Then we're going to have the same folder name. Now, the folder would include several folders, licenses of course, and a very important script that is the OE init build n, which is just a bash script. And this is the Yocto project essentially, which has the Pokey, which is a reference distro of the Yocto project. On a full course, I'm going to actually say what the differences are, but what you need to know is that meta is actually metadata layer from the open embedded project, which is the core of Yocto. And under meta and under actually a lot of other folders, you're going to have things that are called recipes. Recipes, for example, for GTK+, for example, for multimedia, for kernel, and for a lot of other things like GNOME, that let's inspect it now, are going to be textual files that will have several suffixes. Most notably are BB, that actually represent bitbake, which is the build system written in Python. And you a lot of time will have BB append files or any other files like patch files, for example. So we're not going to go into much details of how things are. This is just a quick start guide, but let's have a look at a couple of metadata files or so-called recipes. So for example, we have the gconf underscore 3.2.6, which is the PV package version, .bb. And here we have some metadata like the summary, section, homepage, dependencies, that is what you need in order to actually build this one. So they are going to also get build. There are also things called runtime dependencies and recommendations, but we're not going to talk about it right now. And there's the src URI that tells you where to actually get whatever you want to download from. So we have here some Python inline trickery that says, okay, this is like the package version, and we have all kind of files that we are interested in. You're going to see pn, the package name, in this case GNOME, PV package version, and so on. And these are just textual files that actually tells us how to fetch and how to build, which are known as the tasks when we're actually going to build things. So let's have a look at another one. Let's look at recipes of the kernel. So we have several things like the KX, like K-mode for module building, like DTC for device tree. But let's go to the kernel itself, which is Linux. And then we have several files like the Yocto Tiny or the Yocto RT for RT patch. And we have bitbake files, BB, and you have also inc, which are like include files for them. All are textual. We have here K branch and machine that have like the architecture like QEMU ARM, QEMU x86, and so on. And here we have CRC URIs, which are actually going to tell us where to fetch this kernel from. We see that it's git.yoctoproject.org. It's actually not exactly like the vanilla kernel. There are reasons for that. We have which machines the recipe is compatible with, and we have, for example, a device tree. If we're using QEMU ARM v5, then it's actually going to look at the versatile PB board for the QEMU machine itself, if you know that. So having looked at a couple of recipes, after we extracted our tarball, we see that the tarball extracted is 58 megabytes. And now let's go ahead and actually do something with it. So as I mentioned, the OE init build env script is a very important script. And what it does is actually sources all the environment variables required for our use. So we're going to source OE init build env. You're not supposed to run it. In some platforms, you're going to get a warning. Actually, at the time of recording, there is like a little bug in the script that allows you to run it. But if you run it, it will not export the environment variable, so it will not work for you. So instead, we're going to source it, and we're giving it the first one folder as our target folder. So we can see that we actually changed to the directory to give it as a target folder. We see that we can now run bitbake target, and common targets are core image minimal, core image SATO, meta toolchain, meta ID support. And it also tells us that we can also run a generated QEMU image with a command like run QEMU, QEMU x86, which we'll do later. Core image minimal is going to be a Linux distro that is pretty much BusyBox based, that will not have too much graphics. And core image SATO is going to have like a graphical UI and a graphical framework that is called SATO. You can also build GNOME, you can build KDE, you can build your own window manager, desktop manager, but this is of course if you actually know what you do. So after actually running, sourcing the script, we're going to go ahead and have only a conf file, which under conf you will have an important file called local.conf. When you generate it, it's going to have this automatically generated configuration file saying machine equals the name of the machine. This actually correlates to your BSP, which in the past, the default would be QEMU x86, and now it's QEMU x86-64, which means we're going to build a QEMU emulator for x86 64-bit. Now what we want to do is build the target of core image minimal, which is a fully fledged Linux distro that is textual only and build based on BusyBox. We want to actually build it for the machine that we just had, the QEMU x86-64, and we do it with bitbake. However, let's see what we have here. We have a couple of errors. Now, the reasons for the errors is that maybe my machine is not set up properly, but it's not really possible to understand anything from these log files. So just to be sure and to see what's going on, we're going to go ahead and instead of the experience get the code, we're going to go to the get started here and new to the project. Now this is, as I mentioned in the beginning, a very recommended page, and one of the things that we're going to have is the Yocto Project quick build guide, which is going to tell us, for example, what are the requirements of the machine that we need to build and how to set up the machine. So we see that we need like at least 50 gigabytes of free space. We need these kind of versions, and we have build host packages, which is a quick start for what we want to install. So we're going to go ahead and we're now in Ubuntu, so we're going to apt-get install them. And you can see that we actually install all kind of packages and libraries. And it is notable that we require both Python 3 and Python 2. The reason for that is that BitBake, the build tool itself, the build system, actually requires Python 3, and Open Embedded, which knows BitBake uses the Open Embedded framework. Actually, we run BitBake and it parses the Open Embedded framework. This is what makes the basis for the Yocto project. The recipes there and like the processors for them in Python still rely on Python 2. This is why we need both. So now we're going to go ahead and do BitBake core image minimal, and we see that we have a progress. We see parsing recipes and we progress here. So now these are like the packages that we have, all kind of Pythons, EGL Mesa for graphics, Xterm for some reason that we talk like in the course. And after we did this and finished parsing the recipes, we actually have now currently X running task, and then we have Y out of Z, like 109 out of 2664. So we are 5% now into our build. Of course it increases, and we see that we have multiple jobs running. You can see like down, this is a Tmax terminal, and it actually shows that what's running the task is Python 3. So if you look at the lines, you're going to see things like do fetch, do compile, do patch, do unpack, do configure. Later on, you're going to see do package, you're going to see do install, you're going to see do populate rootfs. All these things that start with do are actually tasks. So when we actually go ahead and go over that, and here is like a fast forward where we also have like do compile for Linux Yocto, which is the Linux kernel, then you're going to see that you will have a lot of things and a lot of like package names that you are familiar with, like the binutils, glibc, and so on. So these tasks actually do things that every embedded build system do, which is fetching from the source, from the repository, from the src URI that we saw earlier in the recipe, like unpacking it, that is extracting tarball or checking out the corresponding tag or branch from Git, do patch, applying patches, do configure, for example, for Ubuntu or the Linux kernel, do the configure, like make config, your respective config, and so on. Then do compile will build, and there are also after build things like packagings, like populating the sysroot, and so on and so forth. So every such recipe that you specify, for example, GNOME or like the Linux kernel, will go through a predefined list of phases. At the end of all, you're going to have your final deployed directory, which is going to be under tmp deploy, and you're going to have your final build artifacts. I'm not getting into it in this video, okay? So after you're done, and this is again a fast forward because it will take time, you will see that attempted X tasks, which is exactly the number of tasks you saw like in the beginning on the dashboard. And what you're going to see is that they do not need to be rerun. And in addition to the conf, you're going to now have cache downloads, which is where the tarballs and Git are going to be populated, and astet cache, which is a very important directory that enables you a much faster rebuilds the next time you're going to build the same target architecture and build like the same packages. So this will speed your build dramatically. All the work itself is being done in TMP, where you have, for example, log, which is where you can look at what has been done, if something goes wrong, what didn't go well. And under work and work shared, you're going to have the building folders per se, okay? Now, at the end, as I mentioned before, the build artifacts are going to be under the deploy directory. And if we look at our working directory, that is first one, whatever we sourced the first script to, we can see that the downloads take like 10 gigs, asset cache take around 2 gigs, TMP takes around 26 gigs. So for this build, you're going to need around 40 gigs to build the QEMU x86 64-bit emulator. So as I mentioned earlier, yeah, you need a lot of disk space, and if you build several things, you're going to need a lot of them. Now you can save a lot of time and space if you have multiple builds, if you configure conf local.conf to actually represent the same download and the same asset cache tier for multiple builds. Now I'm not going to get into it right now, but this is like the most common and most important optimization you will want to be aware of if you actually do multiple builds. There are of course all kind of problems with that if you have like if you work like in a team and you have like remote repositories, but we're not going to resolve it now. Now, after building, and this is a fast forward, you can go ahead and run the run QEMU. Now what I have here is that I was running it from tmux. So we can see running bitback-e. This is the kernel that we run. We have a machine QEMU x86-64, file system ext4. The rootfs file is going to be under deploy, images, the name of the machine, and the file. And we have a configuration file for the QEMU boot, which helps us to automate some things. We set network configuration both so that we'll be able like to have network connection to our machine and from our machine, and so that we can do VNC to the machine if we want. And unfortunately, we have here an error. Failed to run QEMU, could not initialize SDL X11 not available. Now, this particular demo is being done on an AWS instance where I did SSH with X11 forwarding, that is SSH-X. So what is wrong here? And why didn't it work? We'll get to it a little bit later. The reason is tmux, but I know it because even if I run xterm and xize, it says, hey, can't open display. So it's not a fault of Yocto Project, okay? So now when I get out of it, like of tmux, and see like xize, then I will see the eyes popping up, you see? So I'm convinced that it's like not Yocto Project fault because even xize and xterm did not work. Now I'll get back to it and I'll say, all right, what happens if like I don't have graphics but I want to run the emulator? I can go ahead and do run QEMU with the no graphic parameter, and then I will see that my kernel is booting. Now init started, it started udev, and soon enough I will have my login prompt. So we have here the login. The default credentials are root without password. Whoops, actually, I accidentally typed ID. So it's going to be root, the login. And now we are actually in our Linux system. So this is the kernel that we built, 5.2.28. And I can go ahead and play around with the machine, see all kind of things. This is pretty much following the Linux standard base hierarchy. And if I go, for example, I did ls several times to user bin and see what ls points to and what other things points to, I can see that they point to, there are links to /bin busybox, which means that this is pretty much a busybox based distro. I can of course have it having any other tools, and that's it. To terminate from that and get back to my terminal, I would do Control A followed by X. Many people don't know how to exit QEMU and use it in inline, like in your terminal with a no graphic parameter, but I did not do that now. Okay, so I mean I do know and I avoided it. All right, so now let's see what how you can actually go ahead and, if you're not in the tmux, prove that if you do not run with the graphic mode, that you can still go ahead and run QEMU with the graphical window. So we're going to do it very soon. I just remind you that we source the OE init build env inside the Tmux, okay? So once I got out of this Tmux terminal, I'm in another terminal. I do not have my environment variables. So I'm going to do the same thing again. So source OE init build env with first one. This is what we already built. So we do not need to rebuild it. Everything will be just as we expect it. And we do run QEMU. And because now X11 actually works, then we will have the QEMU window. However, it will be very, very, very slow in this configuration because my AWS instance does not have nested virtualization supported. So everything that happens when you try to run a virtual machine inside a virtual machine is not very pleasant, is extremely slow, and if you do it like on your own machine, then by the time we got here, you would also already see things that make sense, and you would probably almost get like to the login prompt, okay? So here it's not going to be the case. It's going to be very slow. Let's just patiently go and look over it. So this is how it's going to be. And we can see now that the kernel, we see the slab layer, kernel user page tables, RCU system, and we'll fast forward because it will take quite a lot of time. So let's just do that. So after we've done that, look at the time it takes. Like we've been waiting for like over 200 seconds just because it's like super, super, super slow because of the nested virtualization. So init is booting, please wait booting, and it will still take some time. But you can really see that like you have the time. You can use this privilege of time to see that the kernel log messages appear on the console, which in this case, this is like the screen that you have in the QEMU, right? When you don't do it with graphic. So this is what we have. We have like the HID generic input device. We have the print K, net console. We free the unused kernel image memory right before we run the init process. If you know how init/main.c runs the show when you initialize the kernel. So that is like what you have. So as opposed to the graphic, run QEMU graphic that we did in the beginning, this one did take a little bit more time. So fast forwarding here, we can see that it eventually ended. We can enter our username, root, and play around with the system as we would before. It took some time, but we got there. After we finish with it, we can close the emulator, and that's it.